All right. We are here in New York City. You can see in the background. This is so cool. I'm in New York City.
You actually can't quite tell, because that could just be a building
That's
pretty
true.
much anywhere. But you see a little sliver of Central Park there. The green is Central Park. Nice little oasis amid the buildings.
It's amazing. And Columbus Circle is right here. And we're in the New York Institute of Technology. And I'm with the intelligent and amazing Eve Armstrong with us. Thanks for like meeting up and recording. This is so cool.
I was delighted to get your email. Thanks for stalking me down.
Yeah, Eve, her bio is quite extensive. A lot of science terms I'm not sure about, but I'm eager to learn more about. And I'm excited. Why don't you describe yourself and your backgrounds?
Sure. I'm an assistant professor of physics here at New York Institute of Technology, and I'm also a research associate at the Museum of Natural History, 1 block north, up that way. If that building weren't in the way.
It's over there. We're in the, what room is this? This is the
12th floor boardroom, 1855 Broadway.
The boardroom.
Yes. Very important location.
Yeah, we got this great view. So you do a whole bunch of different things, including theater and science communication.
Maybe I should back up a little more.
So
from an early age, I had these two interests, both science and theater / comedy / writing, science and the arts. And I kind of toggled back and forth between both of them through college. And then after I graduated, I realized I needed to make some sort of a decision. So
yes, the decision.
Yes, the decision. And I chose to try the acting route in the city. Did that for a couple years. Got real tired real fast of having no health insurance and wondering how I was going to pay the next month's rent.
New York, for those that don't know, New York's a little expensive. Just a little bit.
Just a little bit. Compared to everywhere else on the planet or everywhere else in the universe, as far as I know.
Yeah.
And so I applied to grad school for physics. And after 2 years there, missed theater and the city tremendously. I left, I went to San Diego, great program, University of California, San Diego, but just missed the city, missed the lifestyle, missed theater, missed being creative, quit. Started a theater company with my now husband. Yeah. And 3 years after that, realized that if I ever really wanted to kind of lead my own thing or develop my, I'd have to finish my PhD to be taken seriously doing such a thing. So I thought about that for another year and then decided, fine, I'll finish. And then did a couple postdocs in physics and now finally have this amazing position where I can do both. I can do science research, and I started up a workshop 2 years ago for students to learn the art of stand-up comedy and storytelling on stage. And now just this fall, I'm starting an improv class for students. So I've figured out finally how to rope it all together.
Yeah, I want to kind of explore that too, the relationship between art and science. Because I think from the outside, you take the physics and then theater. How does that go together? You know, describe kind of that merge of art and science together.
Yeah. So I actually see tremendous similarity. I get your point, but I see tremendous similarities.
Well, I'm with you. I'm saying on the outside it appears that way.
Oh, so what's my take? Because what I would say is that look at it from the point of view of creativity and innovation and a sort of driven focus to think outside the box is such a cliche thing to say. But I see science and the arts and then everything else.
Really?
For example, just any sort of, for example, medicine. Yeah. Where if I make a mistake in my research, oh shoot, I've lost 24 hours, I have to code this thing up again. Maybe I'll have to rewrite a talk that I'm preparing. Well, in medicine, if you screw up, somebody maybe has died.
Yeah.
So in the arts and the sciences, I feel like it's culture's opportunity to kind of take a break from the seriousness of everyday life. And it's kind of almost cross-training for your brain, where you can let your brain go pretty much anywhere it wants. And no one's going to get hurt. Well, usually, unless you... no one's going to get hurt. Something new is going to come out of it that hasn't existed before. And you're going to be able to share that with people. It's something new.
Yeah.
And so I think that science and the arts are just a perfect combination. Yeah. In a certain context. I mean, sometimes you need to focus on one or the other. I don't bring improv comedy into every group meeting I have in order to, write up this paper that we need to get out. But I love the combination.
Yeah.
In fact, I found that when I do just plain theater, it's less of a challenge than when I realize, oh, there's a theme here, and I need to figure out how to almost trick an audience sometimes into listening to something that on the surface sounds pretty boring and hard, and hard to access. And I think, well, wait a minute, what if I can get them going with a joke or with some funny thing out of left field they don't expect to get in a class, getting them laughing and then kind of tricking them into learning something along the way. And to give you an example, I write an April Fool's satire every April Fool's Day. I post it to this existing open access repository for real scientific articles. And the first one I ever wrote, I was writing up my thesis in grad school. And I was miserable writing this thing up. So this is what I do a lot. I have my real thesis up in one window. And then just to blow off steam, because I'm sick of it, I bring up another window and I'm starting to write a satire of the thing in this other window. And I published that as my first April Fool's article that no one really paid attention to, but then kind of started catching on over the years. And the third or fourth one I wrote, I had friends of mine, it was about machine learning. That's an algorithm we work with in our own research. And I wanted to, blow off steam, as I said, and maybe learn a kind of related technique that I wasn't very familiar with. And if I can make fun of something, that's all the ammunition I need to learn it myself. So I wrote this thing, and some friends of mine who, and some people I'd never heard of actually, wrote to me and said, I would never read one of your actual scientific papers. It sounds like actually kind of boring, but this is great. And that led some of them to actually go back and find my real scientific articles and say, oh, so is this how machine learning works? And I'm like, yeah, kind of. So that's what I mean when I say if you can use the arts or comedy or some creative thing to kind of tease somebody into learning something, that just brings me a lot of satisfaction, a lot of joy. So it makes everything more fun.
Yeah, like pulling something from over here to then use to communicate another idea, right?
Yeah, or to making people open to learning something in the first place, something that otherwise would look very daunting and intimidating.
Yeah. So
making it accessible. That's not the number one reason why I do the comedy stuff. The number one reason is it's my favorite thing. But it leads to some nice outcomes.
So how did you get into astrophysics? How did you decide to pursue that?
I was also, you know what, I'm going to credit my dad. My dad's a very curious guy. I hated science in grade school.
Okay.
The way it was taught. You memorize bold-faced words in a textbook. So I did, I did that fine, but I never really cared. But my dad is a really curious person. He would point out something to me like, oh, look at the icicles, honey, forming on our window. Why do you think that is? Isn't that weird? I say, oh yeah, that is kind of weird. And then, honestly, when I was 16 years old, I was dead set on being an actor and writer. And that was the year that the movie Apollo 13 came out.
Okay.
And I bought it as I would always buy a family gift for the family, but it was something that I secretly wanted anyway, so it was killing two birds with one stone. And I watched, have you seen the movie?
I've seen parts of it.
Okay.
I haven't seen, unfortunately, I haven't seen.
Well, you've seen this part. Take off, lift off.
I'm very aware of it, yes.
Okay. So my dad and I are shopping for Christmas presents. We're in Barnes & Noble. And Barnes & Noble, I don't know if they still do, but they had this big screen where they're playing a movie. And I sat down waiting for my dad. I was done shopping, kind of bored. And they're playing that scene, the liftoff. Okay. And I'm watching it, and they lift off, and I'm realizing that I'm in tears over the idea that we can do that we can figure things out to the extent that we can harness our understanding of the orbital dynamics, Earth-Moon system to build this thing that could, okay, they almost died, but that's not the point. They didn't die, and we can pull this off. And every time I had this conversation with a former physics mentor, every time I see an airplane flying through the sky, I watch it and think, that is a hulk of metal flying through the air. That's amazing. I was just so taken with the fact that we have this ingenuity, this ability. And it starts with being creative and not feeling like you have to think within a certain set of parameters. Well, you do. There are laws of the universe, but they're relatively broad. So I told my parents that night after watching, I brought it and we watched it together. I said, I'm going to be an astronaut. That was it. Wow. I wound up along the way deciding against astronaut, but I started working really hard in school. I never really tried before, and I applied to undergraduate programs with great grades. I got into Columbia. The astrophysics department at Columbia was really small. It was like a little family. I loved it from the beginning. So that's why. And now that I'm hearing my own words, I'm realizing it was a piece of art that got me to pursue science.
Yeah. Isn't that amazing? It's so inspiring.
Yeah.
What kind of research do you do?
I hadn't even prepared to tell you that. And I'm realizing that should have been the example I gave you when you asked the question in the first place. What kind of research do I do?
Yeah. So fast forward,
yeah.
And now the research in the field of astrophysics.
Yeah. So we study how supermassive stars die at the end of their lifetimes. So I'm talking about a supernova event. That's the name for... So stars go through a series of nuclear fusion burning stages where they take lighter nuclei and fuse them into heavier. Okay. Hydrogen into helium, that's what our sun is doing right now. And helium, there's a set of reactions that lead all the way up to iron. In the most supermassive stars, iron, you can get to iron and then you're done. Because once you get to iron, it's no longer energetically favorable to create the next element in the series. And yet they exist. There's gold, see some gold over here. There's aluminum, there's uranium floating around. Where do those elements come from? That's a big open question in astrophysics. And one candidate site for the creation of these elements is the death throes of these supermassive stars. When a star dies, the innermost region of it collapses to a compact object, neutron star or a black hole. Okay. But in the process, the outer layers are blown away in what we call a supernova envelope. Oops, microphone needs to stay here, sorry. And that envelope is a candidate site for the creation of these elements. And we are asking, well, what would the recipe have to be in that cloud for this indeed to be where that synthesis, that nucleosynthesis takes place? And the technique we use to probe this, it's called an inference. That's an umbrella term for harnessing information in available measurements to complete the picture of where those measurements came from. Machine learning is a type of inference procedure. Okay. Machine learning relies on extremely large, dense data sets. We're on the opposite extreme where our available data are very sparse because these explosions come from very far away and we have very sparse evidence of them here. So what we're doing is asking how much can we squeeze out of these measurements to predict backwards to where these measurements came from. And by measurements, I'm talking about neutrinos. These are ghost-like elementary particles.
Okay.
Hold up your hand. Count to 1. There you go, 1. While you were counting to 1, about 1 trillion or 10 trillion or so neutrinos just passed through your hand.
Wow.
They're very hard to capture. Same through the Earth's core, actually. Earth's core is nothing for a neutrino. They're very weakly interacting. They're very hard to capture. And there exist neutrino detectors on Earth, and we are working to ask, well, how much information is contained in what we call the neutrino, what kind of signature is contained in the neutrino measurements at Earth about where these guys came from.
Wow.
So can we infer the physics of the supernova based on these measurements in conjunction with optical and electromagnetic spectrum observations and gravitational wave observations too? I can go into that, but I think I might be sidetracking us a bit.
So
this is a very long, detailed answer to your question.
So we have the neutrinos, which are they smaller than atoms?
Yes.
Okay.
Oh, yes. Much smaller than the constituents of atoms. So you got an atom, then you got a nucleus of an atom,
Okay.
which takes up a very, very small part of the atom. Wish I had 2 hands. And
Here, use my hand.
Okay, well, all right, great. So here's
Okay.
the nucleus. And the electrons orbit the atom, which basically sets the radius of the
Okay.
atom. And to scale it, you would not be able to fit the electron orbital inside this room.
Wow.
And a neutrino is, so within the nucleus now, you've got neutrons and protons inside the nucleus. And a neutrino is orders of magnitude, that is factors of 10, smaller than either of those 2 little guys.
So these are really, really tiny.
Pretty tiny. Yeah.
How do they? So if we have a star that burns out, how in the first place were we able to capture the neutrinos?
So we can't capture a neutrino per se. What we do
Okay.
is we build a physical model of how neutrinos interact with other particles in the vicinity.
Okay.
And what we're observing is evidence that a neutrino has happened by.
So it's like observing behaviors or what happens to other things
Yes.
that we. Okay.
Yes, exactly.
Wow.
Exactly. These neutrino detectors, they're huge tanks of heavy water. I won't go into what that means, but let's just say water.
Okay.
And if a neutrino comes in, well, we're talking many, many in order to be able to see the effect. There's a characteristic kind of radiation that is given off during the interaction that this detector is set up to be able to capture.
Okay.
So if you detect that characteristic signature in the radiation, then you infer, okay, it is more probable than not that a neutrino is responsible for
Okay.
that signature, for that signal.
So as technology accelerates, like right now we're recording on three iPhones, right? As things get smaller and more advanced,
Yeah.
does the science and research start?
Oh.
Yeah.
Oh, absolutely. Oh, my goodness. I just had this conversation with my students in group meeting yesterday. So we're working with a very small scale model of a supernova event. Here's what I mean by that. A real supernova probably gives off on the order of 10 to the 58 neutrinos. That's a 10 with 58 zeros after it.
Oh.
Our model, and you may ask why bother, but our model uses many, many fewer than that. We are actually right now focusing on the interaction of just 2
Okay.
beams of neutrino.
Two out of like the 58.
Well,
or
it's not that silly. It's 2 beams of, let's just say, a ridiculously small number compared to 10 to the 58.
Okay.
but it's useful. It's still it's a useful step. Science is a series of little itty-bitty baby steps.
More than nothing.
It's more
something.
than nothing.
Yeah.
But what we're doing now is this year, what we're looking forward to doing is working in conjunction with people who model larger scale simulations.
Okay.
And what we're still going to hit up against is computational limitations. So, so we are looking at just a handful of neutrinos because we would like to get a handle on that physics before ramping it up to more and more. But at a certain point, we're going to be limited not because of the question we want to ask, but because of the computational expense of being able to do that.
Okay.
So one of my colleagues here works on quantum computing. Yeah. And given what's happened with AI over just the past handful of years, and ChatGPT, my God, what are we going to see emerge and how quickly? And I don't know, that's not my field. I can introduce you to my colleague I'm talking about if you're interested. So, and I don't know how to predict that. I don't know how to predict how much we're going to be able to do. Are we going to be able to simulate a 10 to the 58 neutrino event in my lifetime? I really don't know. I'm not in that line of work, but I'm very curious and excited to see how quickly this accelerates.
So what
I mean by that is how quickly the rate at which computations get easier and easier and easier accelerates. I mean, one of my former mentors will say, do you know how big the computer was that I had when I was your age? You carry that thing around in your backpack like it's nothing. So I couldn't have picked that thing up.
Every time I open up my laptop,
smaller.
I take a moment and I'm just like, I'm so grateful that this machine exists in my lifetime. This is so wonderfully amazing. It's So what do you think that means to like the human story? It's just so phenomenal. Can we solve things like electricity or
Can we solve,
like energy on Earth? Or
you mean not being so reliant on these sources we're using now?
Yeah, like through learning, taking astrophysics and other realms of science and merging it with the technology.
Well, sure, we've already got solar energy. So I'm a little nervous answering the question because this is not my area of specialization. But we've got solar energy and we've got hybrid cars now. I don't know how quickly that's going to start replacing. I was making a joke the other day. Oh yes, I had forgotten my power cord, and my laptop was on its last legs. 10 more minutes left before it died. And so what is that going to look like in 10 years? I really can't tell you. But astronomy and astrophysics has led to our being able to understand how to harness energy from the sun. Yeah. And that's already here. That's been here for what? I'm betraying my ignorance now, maybe 20 years?
You're asking the wrong person. So yeah, what are some of the uses from some of the everyday uses that have come from studying astrophysics?
Everyday uses. Well, okay, here's one example. Let me lump all these things together. There's a way of, let me just say physics. There's a way of training your brain to think about how dynamical systems work. And that in more recent decades, there's a way of figuring out how to translate that into a computing code so that you can get computers to perform tasks that it would take you 100 years to do, that translate to other areas. So for example, one of my very first undergraduate students, I met him through a class. He was the best in the class, so I approached him and said, do you have any interest in research? And he said, oh, yes, but don't you do astrophysics? Kind of like cringing. And I said, yes. And he said, I have to be honest with you. I couldn't care less about astrophysics, but I've heard that you use the supercomputing cluster here. And we do. And I said, yes. And he said, well, what I'd really like to be able to do is I want to go into to neuroscience, into neural prosthetics, And it was interesting because I actually did a postdoc in neuroscience before I started my astro research. And my point is going to be that skills translate. So he said, so what I'd like is to join your group, so long as you don't expect me to learn anything about astrophysics. I really want to learn how to control the supercomputing cluster. I want to learn how to build my own someday, and I want to learn machine learning. I said, great, you're in. And oh, God bless him, he set the whole supercomputing cluster up, you know, our interaction with it. I still don't know how it works because I, like the science questions, I want to give that to the students. So it was just a perfect, it was a perfect relationship. So he got that all up and running, and he's an expert on it now. He's graduated. I have to email him sometimes with questions about how it works because I still haven't bothered to learn. I'm a little bit lazy in that way. So my point is, you can harness the skills from this discipline and take them in many, many new directions. So that's one possible answer to your question.
Yeah.
But there's, go ahead.
Elaborate on supercomputer cluster.
Oh, sorry. Let's go back to computational expense. It takes time for a computer to do a job that you tell it to do. So you have a calculator built into your laptop. Okay, so you type in, you bring up your calculator and you type in 2074 divided by 17.6, because you probably don't want to do that in your head.
Yeah.
And you press enter, and it gives you a result pretty much instantly as far as you're concerned.
Right.
But these codes, these simulations we do, are much, much more computationally expensive. Okay, so hundreds, maybe thousands of lines of code. That takes time for a computer to run. And how much time depends on how much you've got on your machine. So if I wanted to run these simulations on my laptop, we wouldn't be publishing a paper anytime soon. It would take years. The supercomputer is much larger. We run it remotely. So it's got much, much more power. It runs these simulations much faster. And we control it locally from our computers. But we had to set up the means of communication between our computers and the supercomputing.
So the supercomputer, is that a quantum computer?
No, that gets back to another topic we began.
Okay.
Oh, someday. So that's what I meant when I said, oh, where are we going with this? Because to date, our supercomputing cluster, it's very impressive in what it can do, but we can't run a simulation with 10 to the 58 neutrinos. That would crash it. It would take, my students would graduate before we were finished. I am very curious to know how the quantum computing front will develop, because we would love to be able to multiply the efficiency of that cluster by a factor of 1,000, 10,000. And that's where the quantum computer comes in. And that's where the extent of my knowledge stops. But quantum computing is where we're looking in the future.
That's kind of the direction we're,
Yeah. We've got people working on that here. Yeah, not me.
In this building?
In this building, yeah. Oh. That building right over next door.
Okay.
Yeah. Yes, very close.
Oh, that's so exciting.
And at our sister campus on Long Island. Old Westbury, we've got a campus out there too.
Okay. Nonlinear thinking. How important is nonlinear thinking to solving problems?
Okay. Well, nonlinear systems are, let me define nonlinear systems. A linear system, let's define that first.
Yeah, let's back up.
Yeah, let's back up. It's the most simple system you can describe, and it's too simple to really describe any realistic situation that actually exists. A one-to-one, for example. Let's say you want to associate two variables together. My behavior and then your behavior. Okay. A linear system would have to say that either your behavior is completely dependent on mine, or my behavior is completely dependent on yours. So if some independent observer were to come in and observe only me, then they would be able to perfectly predict exactly what you're going to do based only on what I'm doing.
Okay, and that's linear.
That's linear.
Okay.
Now, any realistic already we're just two people. You're asking about solving problems in society in general. We're just two people. Our relationship is already nonlinear because you ask me a question and my response is going to depend on what you've asked me. But then your next question is going to depend on what I just said. Yeah. And my behavior is kind of affected by the way you're behaving. You seem, I came in here pretty nervous for this interview, but you seem like a pretty relaxed person, and that helped me. So it's this sort of chicken or the egg thing, if you will.
Yeah.
Like we're both sort of evolving in time together. So that is the simplest example that occurs to me of a nonlinear system. Every situation that you can think of in society is a nonlinear situation. Historically, because it's computationally difficult to get at, nonlinear systems have been, in many areas, approximated as linear, because then they're easier to investigate. But at a certain point, that becomes like to be a futile means of attack because it's not realistic. So, for example, the system that we study in terms of neutrinos emanating from a supernova event, that's a nonlinear dynamical system. Dynamical in the sense that it's continually evolving in time. Dynamical system. A bunch of neurons in the brain interacting with each other via electrical signals, that's a nonlinear system. A bunch of people interacting in a boardroom, that's a nonlinear system. Have you heard of the 6 degrees of separation rule?
Yes.
That you're related to everybody in the world by just 6, and now with social media, maybe it's even fewer. That's related to the small worlds paradigm. Do you know what I'm talking about when I say small worlds structure? I haven't heard that. It's the idea that there are small worlds of, let's say, people. That there's a family here of like 6 people. There's a family here of 4, and there's a family here of 3. But one of the people in this group knows one of the people in this group. So all the small worlds, if you will, are connected by very sparse connections or synapses. And if you look across different scales of things, so people, neurons...
It's taking the 6 degrees of separation, but scaling it a little bit.
Yeah, so this applies to so I just gave you the example of people.
Yeah.
But if you look at the brain, very, very similar structure. You see very tightly connected kind of wads of neurons here and here and here and here. But then there's a very skinny synaptic connection between one neuron in this wad and one in this one. So that if you zoom way out, you find that the brain is composed of very tightly connected little conglomerations, but they're all somehow connected very sparsely to one another. And then if you zoom even farther out to the observable universe, you see very similar structure, large-scale structure in the universe. Wow. So these are all nonlinear dynamical systems connected in eerily similar ways. So I actually, very long term, I'm very interested in the connection between the way the universe is structured and the way the brain is structured, and the way society is structured. It's
like from the brain, and then it just like keeps scaling to the universe, right?
What I mean is, you see the same kind of architecture, I guess that's the best word to use, on vastly different scales. So large scale structure in the universe, tiny itty bitty structure in the brain, and then in the middle, people. Mm-hmm. Society structures itself in this same kind of way.
It's amazing. Huh. What's something...
But I'm not sure if I answered your question. There are people working on what you just were asking me about treating cultural interactions as nonlinear systems. If you go and Google nonlinear or small worlds culture, nonlinear dynamics society, you'll find things. I haven't ventured far into that, but it's out there. There are people actively working on this. I don't know who they are, So I'm a little bit out of my comfort zone again. But this is an active area. My point is, this is an active area of research among social scientists.
Huh. What's something you're curious about?
Okay.
That's my favorite question. I always love to ask people at the end.
I'm curious about what the best and the most efficient way is to get people excited about science. A lot of the students that there are other things too, but this has been on my mind lately, so it's what occurred to me. I want to say most of the students I meet here, not here per se, just in my whole life experience, and the friends I have and the family I have, think science is a really good thing. It bears great fruit, but it's kind of scary and kind of boring, and not something that they would ever be able to do. And I'm just learning in recent years that the comedy really breaks people down, or breaks that barrier down.
Yeah.
And I want to keep kind of going in that direction, figuring out how to figuring out how to dissolve that barrier that's just completely self-imposed. I don't think I can do this. I just like to bang at that. What else am I curious about? I'm excited about? I'm also wondering when the next supernova is going to go off. We're due. They occur about once every 100 years.
Okay.
Last one was in 1987, and we want more data. So we're sitting around waiting for the next one. Any day now.
It puts an interesting visual in my head of like a bunch of scientists just like sitting around.
Okay, no, we're not.
When does this thing coming?
we got other stuff to keep us busy. We're not just sitting around, but we're looking forward to the day.
Uh-huh. What excites you about the future?
You're going to get an answer that's not science or arts related. It's family related. It's family and friends related. I have 3 little nephews. I'm so excited to see what they become. That's more personal. That excites me much more than the science and the arts angle. But I'm assuming that you're asking me a science and arts question.
It's up for interpretation.
Oh, well, you know what? Let me take that. Let me marry the two. I'm excited to see what my science and engineering and comedy and art students here do with that. I'm sure they're going to take it somewhere weird that never would have occurred to me.
Yeah. That's beautiful. That's awesome. And you recently got funding from the National Science Foundation.
Yes, thank you. Yeah.
That's also incredible.
Convinced them to fund, yeah. So they fund the research, the pure research, and they're supporting the comedy stand-up for science communication. I made the case that this is a terrific way to teach young scientists how to communicate, and I tell my students, it's, you can be a genius and you can do brilliant work, but it doesn't really matter all that much if you can't explain to other people what you're doing and why it's useful. So that was my proposal to the NSF. Let me do this. Let me get students up on stage and teach them how to tell a story to an audience, and it's going to feed back. They're going to be smarter and quicker on their feet. They're going to be able to give a scientific presentation with more pizzazz, if you will, and they won't be terrified at the Q&A afterwards. They'll be able to think on their feet and look at the audience in the eye and not be terrified. And it's going really well. It's a lot of fun. So that's what I meant when I said I'd love to see what these students do with it.
Yeah. That's awesome. Thanks for sitting down and recording with me.
Thank you for inviting me.
This has been so much fun.
Yeah, thank you.
This is great.
I'm glad that you found me.
Yeah, so am I. Thank you.
Thank you.